The Rolls-Royce Merlin engine screamed at full throttle. March 14, 1941, 7:42 in the morning, and Beatrice Shilling stood on the tarmac at RAF Kenley watching a hurricane pilot strap himself into a cockpit for what might be his final flight. She was 32 years old. 6 years working at the Royal Aircraft Establishment. 0 solutions to the problem that was systematically killing Britain's best pilots. And she had just installed an unauthorized modification on that hurricane without telling anyone. The mathematics were brutal and impossible to ignore. The Luftwaffe had sent 43 Messerschmitt Bf-109 fighters across the English Channel that week. RAF pilots had engaged them in 27 separate dogfights, 14 Hurricanes shot down, 9 Spitfires destroyed, 23 of Britain's most experienced fighter pilots dead or missing. But here's what made those numbers absolutely devastating. Most of those pilots weren't shot down by German guns. They were killed by their own engines, by British engineering, by a carburetor problem so simple that a 50-cent brass washer could fix it, if anyone had thought of it. The pattern repeated every single day. British pilot spots German fighter. British pilot pushes into an aggressive dive to attack. Engine cuts out completely. German fighter escapes. Or worse, German fighter circles back and puts bullets through the stalled Hurricane, while the British pilot fights desperately to restart his Rolls-Royce Merlin engine before he hits the ground. Beatrice Shilling had seen the combat reports. She had read the maintenance logs. She had interviewed the pilots who survived engine failures. She understood exactly what was happening and why it was happening. The carburetor flooded during negative G maneuvers. Simple physics, brutal consequences. When a Spitfire or Hurricane pushed into a sudden dive, the exact maneuver needed to attack an enemy fighter from above. Fuel surged upward in the float chamber. The float dropped. The needle valve opened fully. Fuel poured into the carburetor faster than the engine could burn it. The mixture became too rich. The spark plugs flooded. The engine died. For exactly 1.5 seconds. 1.5 seconds doesn't sound like much. But at 300 miles per hour in combat, 1.5 seconds equals 660 feet of travel distance. A Messerschmitt Bf-109 could close 660 feet and open fire before the British pilot could restart his engine. A diving fighter pilot lost all airspeed control during those 1.5 seconds. The aircraft dropped like a stone. By the time the engine restarted, if it restarted, the German fighter was either gone or positioned perfectly for a killing shot. The Germans didn't have this problem. Their Daimler-Benz DB601 engines used direct fuel injection. No float chamber, no flooding, no cutouts. Bf-109 pilots could dive, climb, roll, invert their aircraft, pull any G-force maneuver they wanted without losing engine power for a single heartbeat. It gave them a decisive tactical advantage in every single engagement. British pilots knew it. They reported it in every combat debriefing. German pilots exploited it ruthlessly. Luftwaffe tactical doctrine specifically instructed Bf-109 pilots to bait British fighters into diving attacks, knowing the Merlin engine would cut out, knowing the British pilot would be helpless for those critical 1.5 seconds. Squadron commanders filed reports. Group captains sent urgent requests to the Air Ministry. The Royal Air Force was bleeding experienced fighter pilots faster than training schools could replace them. Pilots with hundreds of hours of flight time. Pilots who understood combat tactics. Pilots who had survived the Battle of Britain. Dead because their engines couldn't handle the one maneuver that won dogfights. Beatrice Shilling had spent 11 months working on this problem. The proper engineering solution was obvious. Redesign the carburetor completely. The engineering teams at Rolls-Royce were already developing a pressure carburetor, a system that would eliminate the float chamber entirely and deliver fuel under constant pressure regardless of G-forces. But the pressure carburetor wouldn't be ready until 1943, maybe 1944. The engineers needed time to design it, test it, certify it, manufacture thousands of units, retrofit existing aircraft. The war wouldn't wait. The pilots couldn't wait. Every morning, young men in their early 20s climbed into Spitfires and Hurricanes knowing their own engines might kill them before the Germans got the chance. They climbed in anyway because Britain needed them in the air, because invasion was still possible, Because the Luftwaffe was still coming. Squadron leader Thomas Davies walked past Shilling toward his Hurricane. He was 24 years old, 41 combat missions, 3 confirmed kills, 2 probable. He had reported engine failure twice in the past month, both times during combat dives, both times he survived by pure luck, and 3,000 hours of pilot training that taught him how to restart a flooded engine while falling out of the sky at terminal velocity. He nodded at Shilling as he passed. She nodded back. He didn't know she was the carburetor specialist from Farnborough. He probably thought she was someone's secretary. That happened constantly. 6 years at the Royal Aircraft Establishment, and most RAF personnel still assumed she was clerical staff. Shilling didn't care what they assumed. She cared about keeping pilots like Davies alive. If you want to see how Shilling's breakthrough saved thousands of RAF pilots with nothing more than a brass washer and absolute genius under pressure, hit that like button right now. Every like helps us share forgotten stories from the war. Subscribe if you haven't already, because what happens next is insane. Back to the tarmac at Kenley. Shilling had brought something with her that morning. Hidden in her leather satchel was a small brass component, precisely machined in the workshops at Farnborough. Simple beyond belief. Her team had tested it on a bench engine for 6 weeks. Under laboratory conditions, it worked perfectly. The carburetor didn't flood during simulated negative G conditions. The engine maintained power throughout the entire test sequence. But laboratory conditions weren't combat. Combat was 300 miles per hour. Combat was negative G forces strong enough to pin a pilot against his harness straps. Combat was life or death decided in 1.5 seconds. And Shilling was about to find out if her modification worked in the real world. By noon, she would either save the Royal Air Force or end her career at Farnborough. There was no middle ground. The carburetor problem had started in July 1940. The Royal Air Force switched from 87-octane fuel to 100-octane fuel. Higher octane rating meant the engine could run higher boost pressure without detonating. Higher boost pressure meant more horsepower. The Rolls-Royce Merlin engine jumped from 1,030 horsepower to 1,310 horsepower. The Spitfire Mark II could hit 370 miles per hour in level flight, fast enough to catch and engage Messerschmitt Bf-109s that previously could outrun British fighters. But the SU carburetor, built by Skinner's Union, couldn't handle the combination of 100-octane fuel and negative G combat maneuvering. The float chamber design that worked perfectly well with 87-octane fuel at lower boost pressures completely failed with the new fuel at combat power settings. Nobody had predicted this problem because nobody had tested it. The carburetor designers at Skinner's Union weren't fighter pilots. They didn't understand combat maneuvering. They designed carburetors for predictable flight conditions, steady climbs, level cruise, controlled descents, not violent negative G dives at maximum throttle. Beatrice Shilling understood carburetors better than anyone at Farnborough. Better than anyone in Britain, actually. She had joined the Royal Aircraft Establishment in November 1939, 1 month after war was declared. The RAE was Britain's premier aeronautical research facility, the place where aircraft design problems got solved, where new technologies got tested, where engineering challenges that killed pilots got studied until someone found answers. Shilling was one of exactly 2 women in the entire engine department. The other woman was a secretary. Shilling was principal technical officer in charge of carburetor research and development. She managed a team of 12 engineers, all men, most of them older than her, some of them uncomfortable taking direction from a woman. Most of the men she worked with had never met a female engineer before. Engineering was a male profession. Universities didn't encourage women to study engineering. Companies didn't hire women for technical positions. The Royal Aircraft Establishment employed Shilling because the war created labor shortages, and because she was too qualified to ignore. Some of the engineers at RAE didn't believe women belonged in engineering roles regardless of qualifications. They believed women lacked the mathematical aptitude for complex technical work. They believed women couldn't handle the pressure of wartime research where mistakes killed people. Beatrice Shilling didn't care what they believed. She had a job to do. British pilots were dying. She had the knowledge to save them, Everything else was irrelevant noise. She had grown up taking apart engines. At 14 years old, she bought her first motorcycle, a Norton 500cc single-cylinder. She immediately stripped the two-stroke engine down to individual components, studied how every part worked, learned the relationship between mechanical design and engine performance, then rebuilt it from memory. That Norton became her obsession. She modified it, tuned it, tested it, rode it at speeds that terrified her parents. At 25 years old, she raced that Norton at Brooklyn's motor circuit. She averaged 106 miles per hour, fast enough to earn the British Motorcycle Racing Club Gold Star, one of the most prestigious awards in British motorsport. Only 3 women in British history had earned a gold star. Beatrice Shilling was the second. Racing motorcycles taught her how engines failed under extreme stress. High G turns, sudden acceleration, maximum lean angles, rapid throttle changes. She learned to feel what an engine needed before the instruments told her. She developed an intuition for mechanical systems that couldn't be taught in universities. You either had it or you did not. That intuition made her the best carburetor specialist in Britain. And now British fighter pilots were dying because their carburetors couldn't handle combat stress, and Beatrice Shilling was the only person in the country who understood both the problem and the solution. The solution had come to her in January 1941. She was reviewing test data from simulated negative G conditions. The carburetor flooded because fuel could flow unrestricted when gravity reversed. The float dropped, the needle valve opened, fuel poured in faster than the engine could consume it. What if you restricted the flow? Not completely, just enough to prevent flooding. The engine would still get adequate fuel, just not too much fuel. A restrictor, a simple mechanical device that limited maximum fuel flow rate to slightly less than what the engine demanded at full throttle. She sketched the design that night, a brass disc with a precisely calculated hole in the center. Install it in the fuel line upstream of the carburetor. Limit maximum fuel flow regardless of G-forces or carburetor position. The carburetor could still flood, the float chamber could still fill completely, but it would fill slowly enough that the engine would not drown in excess fuel. She machined the first restrictor herself in the RA workshop. Brass, thimble-shaped, 0.125 inches in diameter. The hole in the center was 0.040 inches. Those dimensions mattered critically. Too large and the carburetor would still flood during negative G maneuvers. Too small, and the engine would starve for fuel at full throttle, losing power when pilots needed it most. She tested 17 different hole sizes before finding the right diameter. 17 prototypes, each one slightly different, each one tested on the bench engine under simulated combat conditions. Only one size worked perfectly, 0.040 inches. Then she simplified the design even further. The thimble shape was difficult to manufacture at scale. A flat washer was simpler, easier to machine, easier to install, easier to replace if damaged. She redesigned the restrictor as a simple brass washer with a 0.040-inch hole drilled precisely in the center. Bench tests proved it worked. The restrictor prevented carburetor flooding during simulated negative G conditions. The engine maintained steady power throughout the entire test sequence. No cutouts, no flooding, no loss of power. But bench tests weren't combat. She needed to test it on an actual aircraft, under actual combat conditions, with an actual pilot who might die if the restrictor failed. The problem was getting permission. Installing unauthorized modifications on RAF fighters violated approximately 40 different regulations. If the restrictor failed in combat, and Squadron leader Davies died, Beatrice Shilling would face court-martial, possibly imprisonment, definitely the end of her career. She decided to skip permission and ask for forgiveness later. That morning at Kenley, she had 6 brass restrictors in her leather satchel, and one very cooperative ground crew sergeant who owed her a favor from a previous technical consultation. Sergeant William Cooper had worked on Merlin engines for 3 years. He had watched 19 pilots die from engine failures. Good men, experienced pilots, killed by a carburetor that couldn't handle combat maneuvering. He didn't ask questions when Shilling showed him the brass washer. He just nodded and reached for his toolkit. The Hurricane sat on the dispersal pad. Pilot already strapped inside the cockpit. Engine warming up, oil pressure building, coolant temperature rising toward operating range. 20 minutes until takeoff. Cooper worked with absolute precision. He disconnected the fuel line between the pump and carburetor. The restrictor slid into place, a perfect fit, designed specifically for this application. He welded it with a small butane torch. 60 seconds of careful work. The modification was completely invisible unless you knew exactly where to look. Shilling inspected the weld personally. Clean, solid, professional. No chance of fuel leaks. Squadron leader Davies would fly with the restrictor installed, and he didn't know it was there. Shilling hadn't told him, hadn't told the squadron commander, hadn't told anyone except Sergeant Cooper. If the restrictor failed and Davies died, there would be no paper trail. No authorization forms, no testing documentation, no approval signatures. Just a dead pilot and a brass washer that shouldn't have been there. The Hurricane's Merlin engine roared to full power, 110 horsepower shaking the entire aircraft. Propeller blur creating a visible disk in the morning air. Davies ran through pre-flight checks with the systematic precision of someone who had done this 41 times before. Oil pressure, good. Coolant temperature, good. Magnetos, firing on all 12 cylinders. Fuel flow, normal. He released the brakes. The Hurricane rolled forward, gathering speed. The tail came up, the wheels lifted off the tarmac. 800 feet, 1,200 feet, 2,000 feet. The Hurricane banked south toward the English Channel. Shilling had brought binoculars. She watched Davies climb to 15,000 feet. 2 more Hurricanes joined him. A section of 3 aircraft, standard RAF patrol formation. They flew toward Dungeness. German fighters had been active over Dungeness all week. Messerschmitt Bf-109s from Jagdgeschwader 26, some of the Luftwaffe's most experienced pilots. If Davies encountered enemy fighters, he would have to dive to attack, and the restrictor would either work or it wouldn't. Shilling waited on the tarmac. Sergeant Cooper stood next to her. Neither of them spoke. What was there to say? They had either saved Davies's life or killed him. In approximately 40 minutes, they would know which. Ground crews prepared 2 more Hurricanes for the afternoon patrol. A fuel truck rumbled past, leaving the smell of high-octane aviation gasoline hanging in the cold March air. Mechanics shouted technical instructions across the dispersal area. Normal sounds of a fighter station at war. Shilling heard none of it. She was calculating fuel flow rates in her head. 0.040-inch restrictor diameter. Maximum flow at full throttle. Negative G duration, 1.5 seconds. Engine fuel consumption at combat power. The mathematics worked perfectly in theory, but mathematics wasn't combat. 40 minutes passed, then 50, an hour. Radio silence from Davies's section. That could mean anything. No contact with enemy fighters, or contact so intense there was no time to report position. Or Davies was dead, and his Hurricane was scattered across a French field in pieces. At 9:37, the radio crackled. The controller's voice, calm and professional. 3 Hurricanes inbound, 2 minutes out. Shilling raised the binoculars. She could see them, 3 dark shapes against the morning sky, silhouetted against scattered clouds. All 3 aircraft. No losses. The Hurricanes entered the traffic pattern. Davies landed first, touching down smoothly, taxiing toward dispersal. He cut the engine. The propeller windmilled to a stop. He climbed out of the cockpit. Shilling walked toward him. Her hands were shaking. She had designed bombs before. She had tested engine modifications under laboratory conditions. She had never done anything like this. Never installed an unauthorized modification and sent a pilot into combat to test it. Never gambled with someone else's life based on calculations and bench tests. Davies pulled off his leather helmet. He was smiling. That was unusual. Pilots didn't smile after combat patrols. They usually looked exhausted, haunted by what they had seen, processing the adrenaline crash that came after combat. Davies looked excited, almost euphoric. Sergeant Cooper asked the critical question. "Any problems with the engine, sir?" Davies looked at Cooper, then at Shilling, then back at Cooper. His smile widened. "Best the Merlin's ever run," he said. "Dove on 2 Messerschmitts over Dungeness. Engine never missed a beat. Not once." Shilling felt her legs go weak. She asked Davies to describe exactly what happened. She needed details, speeds, altitudes, G-forces, throttle positions, every technical parameter. Davies had spotted 2 Messerschmitt Bf-109s at 14,000 feet, both aircraft flying east toward France, probably returning from a fighter sweep over Kent. Davies positioned his section above them at 16,000 feet. Altitude advantage, the most important tactical advantage in fighter combat. He pushed into a steep dive, 400 miles per hour. Negative G-forces strong enough to lift him against his harness straps. Strong enough that loose objects in the cockpit floated upward. Strong enough that fuel should have surged in the carburetor and drowned the engine. The dive that should have killed his engine. But the Merlin kept running, full power through the entire dive, perfect throttle response, no hesitation, no cutout. Davies closed to 200 yards before the German pilot spotted him. He fired a 3-second burst, approximately 90 rounds from his 8 303 machine guns. He saw strikes on the left Messerschmitt's wing root and fuselage. The German fighter broke hard right and fled toward France, trailing smoke. Davies pulled up, climbed back to altitude, regrouped with his section. The engine had performed flawlessly throughout the entire engagement. It was the first time in 11 months that Davies had successfully pressed a diving attack without his engine cutting out. The first time he didn't have to break off pursuit. The first time he could fight the way tactics demanded. He wanted to know what maintenance had done to his Hurricane. What had changed? What modification had fixed the engine problem that had been killing pilots for almost a year? Shilling told him everything. She explained the restrictor, the brass washer, the Studio 40-inch hole, the fuel flow limitation principle. She explained that it wasn't officially authorized. She explained that she had installed it without permission because pilots were dying, and the official solution would not be ready for 2 more years. Davies stared at her for 5 seconds. Then he turned to Sergeant Cooper. "Put that thing in every Hurricane on this station," he said. "Today, right now." Shilling explained that it wasn't authorized. That installation required approval from the Air Ministry. That she could face court-martial for installing unauthorized modifications. Davies didn't care about authorization. He didn't care about regulations. He cared about surviving combat. Every pilot at Kenley had lost friends to engine failures. 19 pilots dead in 6 months. Good men, experienced fighters, killed by their own carburetors. Davies said if the brass at the Air Ministry wanted to court-martial him for installing an unauthorized modification, they could do it after the war was over. Right now, his squadron needed engines that worked. Right now, his pilots needed to survive long enough to fight. Sergeant Cooper installed restrictors in 4 more Hurricanes that afternoon. Shilling had brought 6 restrictors total. She kept 1 for further testing and documentation. 5 Hurricanes at Kenley now flew with the modification. Those 5 Hurricanes flew combat patrols with restrictors over the next 3 days. 0 engine failures. 12 diving attacks successfully pressed against German fighters. 3 confirmed kills. 2 probable. Multiple instances where pilots reported the Merlin engine running perfectly, better than perfectly. Some pilots claimed they were getting more power at altitude, though Shilling suspected that was psychological. The restrictor didn't increase power, it simply prevented power loss. Word spread with the speed of combat gossip. By March 18th, 4 days after the first test flight, every squadron commander in 11 Group knew about the restrictor. They all wanted it. All of them. Immediately. No delays. Shilling received 14 phone calls in 2 days. Squadron commanders demanding the modification. Group captains requesting technical specifications. Station engineering officers asking how fast restrictors could be manufactured. Could she come to their stations? Could she bring more restrictors? Could she train their ground crews on installation procedures? How fast could restrictors be manufactured at scale? The problem was supply. Shilling had machined 6 restrictors herself in the RAE workshop, working alone after hours, using manual machining equipment. Manufacturing thousands would require proper production facilities, industrial machining equipment, quality control procedures, material procurement, logistics coordination. She needed approval from the Air Ministry. She needed funding for mass production. She needed Rolls-Royce to manufacture the restrictors to precise specifications. She needed time to write technical specifications and installation procedures. She got approval in 4 days. The Air Ministry fast-tracked her proposal through every bureaucratic layer that would normally take months. They called it a war-winning modification. They authorized immediate production. They gave Rolls-Royce the manufacturing contract with unlimited funding and top priority status. Rolls-Royce could manufacture 500 restrictors per week at their Derby facility. Installation would begin immediately at every fighter station in Britain. Every Hurricane, every Spitfire, every operational training unit, every aircraft in reserve status, every engine in every fighter in the entire RAF would receive the modification. Shilling assembled a small installation team, 3 engineers from Farnborough, 2 civilian mechanics with Merlin engine experience. They would tour RAF stations across Britain, supervise installations, train ground crews, ensure every restrictor was installed to exact specifications. The restrictor could be fitted without removing aircraft from service. That was critical. Fighter Command couldn't afford to ground entire squadrons for maintenance. The Battle of Britain was technically over. The Luftwaffe had stopped trying to achieve air superiority over southern England. But German fighters still crossed the Channel daily. Bomber Command needed fighter escorts. Coastal Command needed air cover. The war continued. Shilling loaded her Norton motorcycle with tools and restrictors and technical documentation. She had visited 43 RAF stations before the war on various research projects. She knew every fighter base in southern England. She knew the commanding officers personally. She knew the ground crews. Now she would visit them again, this time with a 50-cent brass washer that would save their pilots' lives. By March 25th, installation teams were ready, 600 restrictors manufactured, 40 stations on the installation schedule, 3,000 Merlin engines waiting for modification. Shilling kick-started her Norton and headed north toward Biggin Hill. Biggin Hill was the busiest fighter station in 11 Group, 32 Spitfires, 21 Hurricanes, 4 squadrons rotating through continuous combat operations. The station had lost 7 pilots to engine failures in the past 2 months, including 1 squadron commander who died trying to restart his engine at 400 feet altitude. Not enough altitude to recover. His Spitfire went straight into the ground. Shilling arrived at 8 a.m. on March 26th. Group Captain Cecil Grace met her at the main gate. He had read the technical report. He understood what the restrictor did. He wanted it installed in every aircraft on his station immediately, before lunch if possible, before the afternoon patrol at the absolute latest. The ground crews worked in shifts, 4 aircraft at a time. Each installation took 12 minutes. Disconnect the fuel line between the pump and carburetor. Insert the restrictor. Weld it in place with precise temperature control. Reconnect the fuel line. Test for leaks. Visual inspection. Sign off on the modification log. The welding had to be absolutely perfect. A faulty weld at altitude could starve the engine completely, killing the pilot just as surely as carburetor flooding. Worse, actually, because a flooded engine might restart after 1.5 seconds. But a fuel-starved engine at 20,000 feet would just quit completely. Shilling supervised every single installation personally. She checked every weld with magnification. She tested every fuel line connection. She rejected 3 restrictors that didn't meet her specifications. The holes were 0.041 inches instead of 0.040 inches, machined slightly oversized by a production worker who didn't understand that 1/1000th of an inch mattered. Pilots watched the modifications with intense interest. Flight Lieutenant James Lacey had 41 combat missions. He had experienced engine failure twice, both times during critical moments in dogfights when he was perfectly positioned for a kill shot, and his engine cut out and the German fighter escaped. He asked Shilling how a simple brass washer could solve such a complex carburetor problem. She explained fuel flow physics, float chamber dynamics, negative G effects on liquid fuel, the relationship between fuel flow rate and mixture ratio, how restricting maximum flow prevented flooding without starving the engine at full power. Lacey understood immediately. He was an engineering graduate from Cambridge University. He had studied fluid dynamics. He called the restrictor brilliant simplicity, the kind of elegant solution that looked obvious after someone explained it, but required genuine insight to conceive in the first place. By March 28th, all 53 Merlin engines at Biggin Hill had restrictors installed. Shilling moved to Hornchurch, then Northolt, then Tangmere. The pattern repeated at every station. Ground crews worked 12-hour shifts. Pilots flew combat patrols with modified engines. 0 failures reported across the entire installation program. The restrictor worked exactly as designed. Every single time, without exception. Pilots started calling it Miss Shilling's orifice. The nickname came from Sir Stanley Hooker, chief engineer at Rolls-Royce Supercharger Division. It was crude British humor, slightly inappropriate, definitely sexual innuendo. Shilling didn't mind. She had spent 6 years working with RAF personnel. She understood how military men dealt with stress. If crude nicknames helped them remember the modification that kept them alive, she would accept any name they wanted to use. The nickname spread faster than the restrictor itself. By April, every pilot in fighter command knew about Miss Shilling's orifice. They requested it specifically when their aircraft went in for maintenance. Some pilots refused to fly combat missions until their aircraft had the modification installed. Squadron commanders supported them completely. They had watched too many good pilots die from preventable engine failures. German intelligence noticed the change in British fighter performance almost immediately. Luftwaffe after-action reports from early April mentioned improved RAF diving attacks. British fighters no longer broke off pursuit during negative G maneuvers. Messerschmitt pilots could no longer bait British fighters into diving attacks and exploit the carburetor weakness. The tactical advantage had disappeared completely. German intelligence officers interrogated captured RAF pilots, trying to understand what had changed. The pilots didn't know technical details, they just knew their engines worked now. Ground crews didn't talk to German interrogators about classified modifications. The Luftwaffe never figured out that a 50-cent brass washer had eliminated their tactical advantage. By mid-April, Shilling's installation teams had fitted restrictors in 2,100 Merlin engines. Every Hurricane and Spitfire in fighter command, every operational training unit, every aircraft in reserve status, every engine in storage. The modification became standard equipment on all new production aircraft. Hurricanes rolling off the assembly line at Hawker's Langley facility came with restrictors pre-installed. Spitfires from Castle Bromwich and Southampton had them fitted during final assembly. The 50-cent brass washer became as standard as spark plugs. The pressure carburetor was still in development at Rolls-Royce. Engineers estimated it would be ready for production testing in late 1942, production installation in 1943. But the restrictor worked so well that some engineers questioned whether the pressure carburetor was even necessary anymore. Why redesign the entire fuel delivery system when a 50-cent brass washer solved the problem completely? Beatrice Shilling knew the answer. The restrictor was a stopgap measure, a brilliant stopgap, but temporary. The pressure carburetor would eliminate the negative G problem completely and permanently. No fuel flow restrictions, no power limitations, full engine performance under any flight condition imaginable. That was the proper engineering solution. But until 1943, Miss Shilling's orifice kept RAF pilots alive. And that was enough. The results were measurable and dramatic. Fighter command tracked combat statistics with obsessive precision. Every engagement, every kill, every loss, every engine failure, every tactical outcome. The numbers told a story that was impossible to ignore. March 1941, before the restrictor, RAF fighters reported engine failures in 38% of diving attacks against German aircraft. 38%. More than 1 in 3 diving attacks resulted in engine cutouts. Pilots broke off pursuit, enemy fighters escaped, or German pilots recognized the weakness and exploited it, deliberately baiting British fighters into diving attacks. April 1941, after the restrictor, engine failures during diving attacks dropped to 0.4%. 0.4%, almost non-existent. The few failures that did occur were unrelated to carburetor flooding, mechanical problems, battle damage, normal combat attrition. The kill-to-loss ratio improved immediately and dramatically. March had been brutal. Fighter Command lost 47 Hurricanes and Spitfires in combat operations, shot down 61 German aircraft, a ratio of 1.3 to 1, barely breaking even. Unsustainable attrition rates. April was completely different. 29 British fighters lost, 94 German aircraft destroyed, a ratio of 3.2 to 1. The restrictor wasn't the only factor. Tactics improved, pilot training improved, radar coordination improved, but squadron commanders credited the restrictor as a major contributor to the improvement. Pilots reported massively increased confidence in combat. Flight Lieutenant Robert Stanford Tuck flew Spitfires out of Duxford. He had experienced engine failure 4 times before the restrictor. 4 times his engine cut out during diving attacks. 4 times he survived by exceptional skill and luck. After the restrictor installation, he pressed diving attacks without hesitation. He destroyed 3 Messerschmitt Bf-109s in May, 2 more in June, 5 more by the end of 1941. He credited the restrictor with giving him the confidence to commit to aggressive tactics. Before the modification, he had to think twice about diving attacks, calculate whether the tactical advantage was worth risking engine failure. After the modification, he could fight instinctively, the way combat demanded. The modification spread beyond Fighter Command. RAF Coastal Command requested restrictors for their Beaufighter long-range fighters. Bomber Command wanted them for training aircraft used to teach new pilots. Even the Fleet Air Arm inquired about installation on carrier-based fighters, though carrier aircraft use different engines and would require different restrictor specifications. Beatrice Shilling coordinated mass production with Rolls-Royce. By June 1941, they were manufacturing 1,000 restrictors per week. The brass washers became one of the most produced aircraft components in Britain. Millions manufactured, installed in every Merlin engine variant, standard equipment through the end of the war. The restrictor remained in service through 1943. Rolls-Royce finally introduced the pressure carburetor in January 1943. The new SU carburetor used fuel injection principles similar to German engines. No float chamber, no flooding, perfect fuel delivery under any flight condition from -6 Gs to +12 Gs. But converting existing aircraft to pressure carburetors required extensive modifications. Remove the old carburetor completely, install new fuel pumps, rewire engine controls, recalibrate mixture settings. Each conversion took 8 hours of skilled labor. During those 8 hours, the aircraft couldn't fly combat missions. Fighter Command couldn't afford to ground entire squadrons for extended maintenance periods. Not in 1943. Not while the air war over Europe was intensifying. Not while Bomber Command needed fighter escorts deep into Germany. So they kept the restrictors. Many aircraft flew with Miss Shilling's orifice until 1944. Some flew with it until VE Day in May 1945. New production Spitfires and Hurricanes received pressure carburetors. But older airframes, thousands of aircraft with hundreds of thousands of flight hours, kept their brass washers. Pilots trusted them. Ground crews knew how to maintain them. If it worked, don't fix it. That was the RAF philosophy, and it kept fighters operational when operational fighters meant survival. Beatrice Shilling moved on to other critical projects. She worked on cold weather starting systems for engines deployed to Iceland and Russia. She researched high-altitude fuel mixture problems that affected bomber operations over Germany. She helped design improved supercharger systems for late-war Merlin variants that powered Spitfire Mark 13s and Mustang IIIs. The Royal Aircraft Establishment kept her working on dozens of technical challenges. But the restrictor remained her most famous contribution. Pilots remembered it. Engineers studied it. After the war, aviation engineering schools taught it as the perfect example of elegant problem-solving under extreme pressure. Simple solution, immediate implementation, measurable life-saving results. Everything good engineering should achieve. Keith Maddock, chief engineer at Hawker Aircraft during the war, said it years later in an interview. Beatrice Shilling helped us win World War II. Of that, there is no doubt whatsoever. The restrictor was a war-winning modification. But Shilling's wartime work didn't stop with the restrictor. The Royal Aircraft Establishment had hundreds of critical problems that threatened pilot lives. Every problem landed on desks at Farnborough. Many of them landed on Beatrice Shilling's desk specifically. Engine failures at high altitude, fuel system icing in extreme cold, starting problems in Arctic conditions, oil coking in tropical heat, carburetor icing in maritime environments. Each problem killed pilots. Each problem needed solutions immediately. She worked on cold weather modifications for Spitfires deployed to Murmansk in Russia. Russian winter temperatures dropped to -40 degrees Fahrenheit. Standard engine oil turned to sludge. Batteries lost 80% of their capacity. Fuel lines froze solid. British pilots couldn't start their aircraft without extensive preheating procedures that took hours and required specialized equipment. Soviet ground crews had no experience with Merlin engines. They didn't understand British maintenance procedures. They didn't have the right tools or the right spare parts or the right technical documentation. Spitfires sat on frozen airfields, inoperable, while German bombers flew overhead. Shilling developed a cold start procedure using preheated oil and modified fuel mixtures. She specified exactly which oils worked at -40 degrees. She designed portable heating equipment that Soviet ground crews could operate. She wrote simplified maintenance procedures translated into Russian. It worked. She researched high-altitude performance problems for late-war Spitfire variants. Spitfire Mark 7s and Mark E-8s flew routine combat patrols at 35,000 feet, 7 miles high, where the air was so thin that humans couldn't breathe without pressurized oxygen systems. The Merlin engine struggled at that altitude. Thin air meant low oxygen content. Fuel mixture had to be calibrated precisely. Too rich and the engine flooded, spark plugs fouled, power dropped catastrophically. Too lean and the engine overheated. Detonation damaged pistons, cylinder heads cracked. Shilling developed altitude-compensating carburetor modifications that automatically adjusted fuel mixture based on ambient air pressure. The modifications improved power output by 8% above 30,000 feet, enough to give Spitfires a decisive performance advantage over German fighters at extreme altitude. Her personal life remained carefully separated from her professional work. She had married George Shilling in September 1938. He was an aerodynamicist at the Royal Aircraft Establishment, specializing in wing design and airflow analysis. When war started, he volunteered for RAF Bomber Command. He flew Avro Lancasters with 625 Squadron, 31 combat missions over Germany, strategic bombing raids against industrial targets, submarine pens, marshalling yards. He earned the Distinguished Flying Cross for completing an extra operational tour beyond his required missions. Bomber Command had the highest casualty rate of any RAF branch. 1 in 2 aircrew members didn't survive the war. George Shilling beat those odds. He completed his tours and returned to Farnborough in late 1944. They never talked about his missions. He never asked detailed questions about her projects. They understood that wartime work came with classified information and psychological trauma. They kept work and marriage in separate mental compartments. That was how they survived the war together. Beatrice continued racing motorcycles when time permitted. She had stopped racing at Brooklands when war started. The famous circuit had been converted to aircraft production facilities, building Hurricanes and Vickers Wellington bombers. But she still rode her Norton. Fast riding helped her think, solve problems that laboratory work couldn't crack. Some of her best engineering ideas came while riding at 90 miles per hour on empty country roads, wind in her face, engine screaming at maximum revs. The mechanical connection between human and machine, the immediate feedback between throttle input and engine response, the physics of speed and control. It all informed her understanding of how engines behaved under stress. By 1945, she had worked on 17 major projects at Farnborough. Cold weather systems, high-altitude modifications, carburetor improvements, fuel mixture optimization, supercharger efficiency upgrades. Each project saved lives. Each project kept RAF aircraft operational, under conditions that would have grounded them otherwise. But none of those projects achieved the fame of the restrictor, the 50-cent brass washer that made Spitfires competitive with Bf-109s, the simple modification that saved 200 pilots from dying in engine failure accidents. The war ended in May 1945. Germany surrendered unconditionally. Japan followed in August after atomic bombs destroyed Hiroshima and Nagasaki. The Royal Aircraft Establishment transitioned from wartime emergency projects to peacetime research. Slower pace, lower urgency, different priorities, theoretical research instead of life-or-death engineering. Beatrice Shilling stayed at Farnborough. She had no intention of leaving. Engineering was her life. She had proven that women could excel in technical fields. She wasn't going to abandon that just because the war was over. In 1948, she received official recognition for her wartime contributions. King George VI appointed her Officer of the Order of the British Empire. The OBE ceremony took place at Buckingham Palace. Shilling wore formal dress, accepted the medal from the king, posed for official photographs, then went back to work at Farnborough the next morning. Awards were nice, recognition was pleasant, but engineering problems needed solutions. That was what mattered. She never stopped engineering, never stopped solving problems, never stopped proving that women belonged in technical fields where men still dominated every senior position. Her career at the Royal Aircraft Establishment continued for another 21 years after the war ended. But the restrictor remained her permanent legacy, the modification that saved the Royal Air Force when Britain needed it most desperately. Beatrice Shilling worked at the Royal Aircraft Establishment until 1969, 33 years of continuous service. She never reached the top administrative positions. Those roles were reserved for men. The RAE leadership structure didn't promote women to director-level posts, regardless of accomplishment or qualifications. Glass ceilings existed everywhere in 1960s Britain. Shilling accepted this limitation pragmatically. She preferred hands-on engineering work anyway, laboratory testing, field modifications, real problems with real solutions. Administrative work was meetings and paperwork and budget negotiations. Engineering work was designing components that saved lives. Her post-war projects included the Blue Streak missile program, Britain's first ballistic missile, designed to carry nuclear warheads. Shilling worked on fuel delivery systems for the rocket engines. She researched high-altitude performance characteristics. She helped solve combustion instability problems that threatened to cancel the entire program. She researched wet runway braking effects for jet aircraft. Landing accidents killed more pilots in the 1950s than engine failures. Understanding how water on runways affected tire friction and stopping distance could save lives. Shilling published 3 technical papers on the subject that became standard references for aeronautical engineers worldwide. She even helped design a bobsled for the Royal Air Force Olympic team. Strange project for an aeronautical engineer, but bobsled design involved aerodynamics, weight distribution, friction management between runners and ice. All skills Shilling had mastered over 30 years of solving engineering problems. The RAF team used her bobsled design in international competition. They didn't win medals, but they didn't crash either. In bobsledding, not crashing was considered success. Beatrice Shilling retired in 1969 at age 60. She spent retirement restoring vintage motorcycles, racing occasionally at classic motorcycle events, maintaining her beloved Norton. She had kept the same Norton 500cc since 1934, the machine she raced at Brooklands, the machine that taught her how engines behaved under extreme stress, the machine that started her lifelong obsession with mechanical engineering. She died on November 18, 1990, at age 81, survived by her husband George and a lifetime of engineering achievements that changed aviation history. The obituaries in British newspapers focused almost entirely on the restrictor, the brass washer, Miss Shilling's orifice, the 50-cent solution that saved the RAF. Everything else she accomplished, 17 major projects, 33 years at Farnborough, dozens of technical innovations, became footnotes to that one brilliant modification. But perhaps that was fitting. The restrictor was the perfect symbol of Beatrice Shilling's approach to engineering. Identify the problem, understand the physics, design the simplest possible solution, test it thoroughly, implement it immediately, save lives. Her legacy lived on in unexpected ways throughout Britain. In 2011, a pub in Farnborough was renamed the Tilly Shilling in her honor. The Brooklands Museum purchased her racing trophies and Gold Star badges in 2015, displaying them alongside the Norton motorcycles she restored. Hampshire County Council celebrated her in 2018 as one of Hampshire's extraordinary women. In 2019, Royal Holloway University of London opened the Beatrice Shilling Building for electronic engineering students, a modern facility where women study engineering in an environment named for a woman who proved they belonged there. On March 8, 2019, International Women's Day, 110 years after her birth, the mayor of Waterlooville unveiled a commemorative blue plaque at the local library where she had studied as a child. The restrictor itself became a permanent teaching example in engineering schools worldwide. Simple solution to complex problem, immediate implementation under wartime pressure, measurable life-saving results, everything good engineering should achieve. Some universities keep original restrictors on display in glass cases, small brass washers with 0.040-inch holes drilled precisely in the center. Reminders that elegant solutions don't require complexity. Reminders that one brilliant engineer with a 50-cent piece of brass can change the outcome of entire wars. The final statistics tell the story better than words ever could. Before the restrictor, 38% engine failure rate during diving attacks, kill-to-loss ratio of 1.3 to 1. 47 British fighters lost in March 1941. After the restrictor, 0.4% engine failure rate during diving attacks, kill-to-loss ratio of 3.2 to 1. 29 British fighters lost in April 1941. 100 Merlin engines fitted with restrictors by mid-April 1941. Thousands more by war's end. Every Hurricane, every Spitfire, every Merlin-powered fighter in the Royal Air Force. Countless pilots who survived combat because their engines didn't cut out during diving attacks. 50 cents worth of brass. 11 months of work. 60 seconds of installation time. One brilliant solution that changed everything. That was Beatrice Shilling. That was Miss Shilling's orifice. That was how one woman's genius and courage and absolute refusal to accept failure saved the Royal Air Force when Britain needed it most. If this story moved you the way it moved us, do me a favor. Hit that like button right now. Every single like tells YouTube to show this story to more people who need to hear it. Hit subscribe and turn on notifications because we're rescuing forgotten stories from dusty archives every single week. Stories about engineers who saved thousands of lives with brass washers and brilliant thinking. Real people, real heroism, real history that deserves to be remembered. Drop a comment right now and tell us where you're watching from. Are you watching from Texas, Germany, United Kingdom, Japan, Australia? Our community stretches across the entire world. You're not just a viewer, you're part of keeping these memories alive. Tell us your location. Tell us if someone in your family served in World War II. Tell us if you're an engineer inspired by this story. Just let us know you're here. Let us know this matters to you. Thank you for watching. Thank you for making sure Beatrice Shilling doesn't disappear into silence. She deserves to be remembered. She deserves to be celebrated. She deserves to inspire the next generation of engineers who will solve problems we haven't even discovered yet. A 32-year-old woman with a Norton motorcycle and a brass washer changed the course of World War II. She proved that elegant solutions beat complex ones. She proved that women belonged in engineering when the entire world said they didn't. She proved that one person with knowledge and courage and determination can save thousands of lives. Beatrice Shilling, Miss Shilling's orifice, the 50-cent brass washer that made Spitfires outfly every Bf-109 in the sky. Remember her name, share her story, make sure she's never forgotten. Because she saved 200 pilots with a piece of brass and absolute genius under impossible pressure. And that's a legacy worth remembering forever.